How's it going, everyone? In this video, we're going to be discussing how to determine the density in the molar mass by using these ideal gas laws that I discussed in the previous video. And so the first thing I need to, kind of point out is the fact that in your book, they do have these two equations for density and for molar mass. In my slides that I have posted on Blackboard, I also go through and I show you how these equations were, or these formulas, were actually kind of developed using the ideal gas law. I actually am not going to go through in this video and talk about that, so please, I do suggest that you read the book and you check out my slides available on Blackboard. It shows you kind of how these equations were developed, but my whole case that I'm going to provide here is that it doesn't really matter if you memorize these equations or not. If you know PV equals nRT, that's all you really need to know for these two. And so in these next two questions, or practice problems, I'm going to demonstrate how you can use these two equations in order to solve for your density and for the molar mass. Or if you don't have time to memorize these, do the same exact math that we've been doing since day one using PV equals nRT in order to solve for exactly the same thing. And so first example has to do with the density. And so I want you to determine the density in grams per liter of CO2 and the number of molecules per liter at STP. And so the first thing you need to remember, as I mentioned in the previous video, STP stands for standard temperature and pressure. And so standard temperature is going to be 0 degrees Celsius, but more importantly, 273.15 Kelvin. Your standard pressure is going to be 1 atmosphere. Additionally, using some concepts that we discovered in the previous chapters, if you're given a molecular formula like CO2 and a periodic table, or if we give you the atomic masses of these, you can very easily determine the molar mass of your CO2. Because we know in CO2 there's 1 carbon, 2 oxygens. Carbon has the molar mass of 12.01. Oxygen has the atomic mass of 16. And so we know that the molar mass of our CO2 is going to be 44.01 grams per mole. And last but not least, since we're talking about gases, R. R is never going to change. R is always going to be your 0.0821 atmosphere liters per mole Kelvin. And so please note, I didn't give you any of these numbers directly. You just need to be able to first remember what STP is, 2, remember what the ideal gas constant is, and 3, remember the good old days when all you're asked about is solving for molar mass. But if you're given a molecular formula and the masses of these one way or another, you can determine the molar mass of the complex. And so if you memorize that equation for density, density equals the molar mass times pressure over RT. And so if you memorize this, this is nothing more than a plug and chug problem. We have the molar mass here in grams per mole. We have our pressure in terms of atmospheres. We have our R in the good old atmosphere liters per mole Kelvin. And finally, we have our temperature in terms of Kelvin. And so if you have this equation memorized, plug all your values in. And just to prove to you I'm not completely lying, here I show you how these units actually cancel out. And so your moles on top cancel moles on the bottom. Your atmospheres on top cancel atmospheres on the bottom. Your Kelvin here cancels out with a Kelvin on the bottom. And your overall end result in terms of units is grams on top, liters on the bottom, or by definition, we are looking at 1.96 grams per liter, which is the definition of density. And luckily for us, that's what I actually ask for up here when I say find the density in grams per liter. But the other half of this question, I'm asking to solve for number of molecules per liter. And so here, half of the work is already done for you because our answer is already in per liter, and I'm asking for it to be in per liter. And so the divided by liters part's already taken care of. But if I want to know something about number of molecules, we have to, again, go back to chapter 3 or 4 and remember how to go from grams of a substance to the number of molecules of a substance. And so here, just using the density that we just solved for, we can rewrite this as 1.96 grams of CO2 per 1 liter of CO2. Or this situation, per liter is already taken care of, so we just need to fix the stuff on the top and in the numerator. And so here we know how to go from mass to moles using the molar mass. And so here we can go from grams, cancel out with grams, and now we're sitting at moles per liter, which by definition would be molarity. But we're not looking for molarity. We are looking at molecules per liter. So how do we go from moles to molecules? Remember Avogadro, before he came up with some gas laws, he was famous for this crazy number of 6.022 times 10 to the 23 molecules per 1 mole. And here we can cancel out moles of CO2 with moles of CO2, and now we're sitting at molecules per liter, which is what the question is asking for here. So, if you remember, density equals the molar mass times pressure over RT, you just need to make sure that, as I've mentioned several times by now, pressure needs to be in atmospheres, temperature needs to be in Kelvin, R is always going to be in the same units all the time anyways. But say you don't remember this equation, and so as you're reading through this exam question, you're panicking because you can't remember density equals molar mass times P over RT. Who cares? It's completely fine if you remember PV equals nRT. And so let's just wipe this all clean. And so please notice, same questions, same variables that we already know, but in this case, instead of using that density equals molar mass times pressure over RT, let's just use PV equals nRT. For this one, pressure, we already know it in 1 atmosphere. Temperature, we already know is going to be our 273.15. R, we already know is 0.0821. And so out of PV equals nRT, we are assumingly missing volume in moles. But great thing about the way this question was written is I'm asking for density in terms of grams per liter. I'm asking for the second half in number of molecules per liter. And so you guys have to ask yourself, in terms of density, per how many liters? And in this problem, the number of molecules per how many liters? In order to keep our math in our brain a little bit easier, we can safely assume that if I'm asking about something per liter and per liter, we can assume our volume is going to be very safely at 1 liter. And so here, now we know V as well. And so we know pressure, we know volume, we know temperature, we know R. The only thing we don't know is N. And so we can set up our equation, PV equals nRT, plug in our pressure of 1 atmosphere. Plug in our volume of 1 liter, again, just because the way the question stated, I'm asking about density in grams per 1 liter. I'm asking about number of molecules per 1 liter. And so if we solve for this in per 1 liter, we already have our answer in the form that we need it. And so in this case, R, never going to change. Temperature, 273.15 Kelvin, came from the STP. And so we can just plug and chug for all these values, solve for our N, and I end up with 0.04459 moles of CO2. Again, you need to ask yourself, moles of this gas per what? And again, answer is per 1 liter. And so we know moles per 1 liter. In order to go to density, we need to use just the definition of what density is, or grams per 1 liter. And so using the molar mass, we can convert our moles into mass, and we have our unit as grams per liter. Now take a second, rewind this video a little bit, and you'll notice that this 1.96 grams per liter is the same exact number on the previous slide whenever I was asking about density. But we're not done yet. Number of molecules per liter. As I mentioned, we already have this value as moles per liter. We know how to go from moles to molecules using Avogadro's number, so we can again multiply this conversion. Moles will cancel out moles, and our final answer is now in terms of molecules per liter. Luckily for us, same exact number from the previous slide. And so as I mentioned very beginning in this video, both the equations, that density and the molar mass that are shown on the second slide I showed you, both of them were derived using the PV equals nRT equation, which inherently brings along with it, if you know PV equals nRT, you can still solve for these values even if you don't memorize those equations for molar mass. For density. Molar mass, same exact idea here. So, if there's an organic chemist isolates a colorless liquid from a petroleum sample, she places the liquid in a pre-weighed flask and puts the flask in boiling water, causing the liquid to vaporize and fill the flask with gas. She closes the flask and reweighs it. She obtains the following data, and from this data, I want you to calculate the molar mass of the liquid. And so the mass of the flask is 77.834 grams. The mass of the flask and the gas is 78.416 grams. So the main issue with these two numbers is you need to understand and realize we're only interested in the gas. We only want the molar mass of the gas. We do not care anything about the container or the flask that this gas is sitting in. And so one pitfall that a lot of students happen to get into is they just start seeing masses and they just kind of start willy-nilly throwing them into their equation without actually understanding what the volume or what these masses are asking about. And so we'll fix the mass issue here in a second. Volume, which I tell you is the volume of the flask and also of the gas, is 213 milliliters. Your temperature is going to be 100 degrees Celsius and pressure is going to be 754 torr. And so as I mentioned, we'll deal with the gas here in a second, but you also need to make sure your other units are in the correct form. Meaning volume needs to be in liters, temperature needs to be in Kelvin, your pressure needs to be in atmosphere. And so using the same conversions we've done from the beginning of this chapter, or even all the way back in chapter 3, we know how to convert from milliliters to liters. Divide by 1,000, again, to go from milliliters to liters, not the other way around. For our temperature, add 273.15 to go from Celsius to Kelvin. And then pressure and torr, using the conversion of 1 atmosphere equals 760 torr, we know how to go from torr to atmospheres. And so if we want to know the mass of our gas, we need to subtract the mass of the gas in the flask minus the mass of just the flask to give us the mass of just the gas. Now in the volume in terms of milliliters, convert from milliliters to liters. We know our temperature in Celsius to convert from Celsius to Kelvin. We know our pressure in torr, convert from torr to atmosphere using the conversion of 1 atmosphere divided or is equal to 760 torr. And so now if you remember the equation, molar mass equals MRT over PV, that's all well and good. If you know that equation, you know your M, you know your R, you know your T, you know your P, you know your V. It all comes down to plug and chug. And so here, the mass of the gas times the ideal gas constant times the temperature of your gas in Kelvin divided by your pressure in atmosphere and your volume in liters. And so here again, using this equation is all well and good. You can calculate 84.4 grams per mole for the molar mass of your gas. But as I've stated before, if you don't want to memorize this equation, then you don't have to waste your time. If you remember, PV equals nRT. So, as I did previously, let's wipe all this clean. All I really kept here is the information we just solved for. So we know the mass, we know the volume in liters, temperature in Kelvin, pressure in atmosphere. And so knowing PV equals nRT, you can see we have a lot of stuff here already kind of given for us. We know our pressure, we know our volume, we know R isn't going to change, we know T, and so the only thing you don't know from PV equals nRT is moles. And so you can solve for moles using the pressure in atmosphere, using the volume in liters, using your temperature in Kelvin, using R in the terms of atmosphere liters per mole Kelvin. We can solve for 0.006896 moles of your gas. And so the last thing you need to do here is just to remember and understand by definition what molar mass is. And so whenever I first introduced the concept of molar mass, I told you it has a very specific unit, and that unit needs to be in grams of your substance per mole of a substance. Or again, molar mass is in terms of grams of your substance, like the mass, per moles of the substance, like the amount of your substance. And so just using PV equals nRT in the definition of what molar mass means, you know grams per mole. We know the grams, we know the moles, and so as I've mentioned before, it's just a plug and chug problem once you have everything in the correct form. Remember, we saw PV equals nRT because we knew the pressure in atmosphere, no volume in liters, no temperature in Kelvin. Moles is always going to be in moles. And so I promise you, no matter how complex these problems look, no matter how long they are, most of the time, the longer the problem is because we are supplying you with as much of the variables, as many of the variables as we can. And so it's basically like, here's 4 out of the 5 variables. Just make sure that, one, everything is in the correct form in terms, again, liters, kelvins, atmospheres, and moles. Beyond that, it's just know PV equals nRT, know how to manipulate that equation in order to solve for whatever you're actually looking for.